All right, welcome back to Mr. P Helps with Calculus. This is Unit 1, Day 3. So defining limits as at infinity and find the limit as it approaches positive and negative infinity. All right, so this warm-up, I'm only going to do one just for the sake of saving time. These are both conjugate questions, so you would need to multiply by square root of x plus 6 plus 3. That's the opposite of what you see here on the numerator. Square root of x plus 6 plus 3. And then what's going to happen is limit as x approaches 3. So we're going to end up getting x plus 6, and then negative 3 times 3 is negative 9. And then on the bottom, we got x minus 3 times square root of x plus 6 plus 3. And then, of course, this is going to simplify down to x minus 3, so that cancels out with that. So you now have 1 over square root of x plus 6 plus 3. I think I put minus there. Okay, so now I can plug in 3 and solve. 3 plus 6 is 9. Square root of 9 is 3. 3 plus 3 is 6. And you're going to end up getting an answer of 1/6 when you plug in 3 into the simplified version. All right, now, so these are some rules for infinity. Now, if you understand what kind of function we're talking about, these kind of just simply make sense. When you have x to an n power, and that n power happens to be an even, like x squared or x to the 4th or x to the 6th, what you'll notice is that these graphs all sort of look like parabolas. Now, there's different translations of them. They each work the same way. However, we're going to be talking about just simply limits as they approach positive infinity and negative infinity, meaning infinitely to the right and infinitely to the left. Now, what you'll notice about all three of these graphs, or anything that has an even exponent, is that as you go left or right, it doesn't really matter, it's going up for infinity. So the answer is going to be infinity basically no matter what, unless there's been some sort of reflection. Then obviously it's going to be going down towards negative infinity. Now, same thing goes when it's an odd number. Now, when it's an odd number, then you know like x cubed looks like this, or x to the 5th looks like this. And what ends up happening is that one side's going up and one side's going down. So in this case, we're going to have an odd function, not an even function. I know that's the terminology that you have heard in the past. So odd function means it's a reflection over the origin, and even functions are reflections over the y-axis. Now, they don't have to be even functions just because it has an even degree, but I digress. That's a whole nother video. Now, basically what I'm trying to tell you is that as one side is going to be going down towards negative infinity, the other side is going to go up towards positive infinity. Just, you know, this is positive, this is negative, and that kind of makes sense when you think about the way the graph looks. And then when we have rational functions, then we know rationals will have some sort of variation looking to this. Now, this would be like the parent function. You can change it in a lot of different ways. But what you'll notice is that the ends will always be getting closer and closer and closer to the asymptotes. In this case, the asymptote happens to be 0. But the asymptote doesn't have to be 0, the horizontal asymptotes. So the horizontal asymptote is what both sides are approaching as you reach infinity and negative infinity. So we're going to use all that information to our advantage. Now, on this first question right here, we want to go, what is happening to the right-hand side? The further we go to the right for infinity, what is happening to this graph? Now, as x is going to the 6th power, let's say we put in a large number for x, and then we multiply that large number times itself, and then times itself again, times itself again. If we multiply it by itself 6 times, that number is just going to keep getting larger and larger and larger and larger. And the higher you make x, the larger it's going to be, and closer it's going to get towards infinity. Now, obviously, it can't reach infinity, because it's just an idea, but that is going to be our answer. All right, now the next one, this happens to be the same thing as 1 over x to the 11th, because this is a negative exponent. Now, what is happening as we go towards negative infinity? Now, what I can do is I can plug in negative infinity in for x. So we have negative infinity to the 11th power. Now, think of, negative a billion, whatever huge number that you can possibly think of. And if we multiply if we multiply by itself over and over and over and over and over again 11 times, it's just going to keep getting bigger and bigger, bigger and bigger. Whether it's a big number or a small number, whether it's positive or negative, let's be honest, really doesn't even matter because this number is so big, like 1 trillionth, let's say. Okay, that's probably the highest number I can possibly think of, right? That is so close to zero, it's unbelievable, right? So whether it's negative 1 over a trillion or positive 1 over a trillion, it really doesn't matter. 1 trillionth is basically so close to zero that we're just going to say it is zero. So that is the limit because that's sort of like the asymptotes. It's never going to reach that asymptote, but it's going to keep getting closer and closer and closer as you go towards infinity. Now, for the next question, we have a polynomial. When you have a polynomial, you really only have to look at the very first piece, and that's really all that matters. The rest doesn't matter. Or the one, I shouldn't say the first piece, the one with the highest degree, because it's not always listed first. And then I'm going to plug in infinity in for x. So that's 3 times infinity to the 7th power. Now, once again, imagine infinity is just a big number. Let's say it's 1,000,000, which is a pretty big number. And you keep multiplying by itself. A big number times another big number times another big number. What's going to happen is that number is just going to get closer and closer to infinity. Now, once again, we're not identifying what the number is. It's just an idea that the more times we multiply it by itself, the closer we're going to get to infinity. And then if I multiply by 3, that's going to make it even closer to infinity. So the answer is infinity. Now, for question number 4, this is a little bit of a tricky question because we have a rational piece and a polynomial piece. So you can't just do this trick up here. It's not the same situation. So I'm going to plug in negative infinity in for, okay, you know what? I'm going to change this from a negative exponent to a positive exponent. So that's actually 1 over negative infinity to the 8th power. Now, I know that looks weird, but that's negative infinity to the 8th power. And then we're going to add 4 times negative infinity to the 3rd power. All right, and then we're just going to break this down piece by piece. Kind of like what I did before. A big number times itself over and over and over and over again. Just going to keep making it bigger. And it really honestly doesn't matter if it's positive or negative. That'll just determine if it's above or below the asymptote. The point is, 1 over a trillion is 1 trillionth, which is so darn close to zero, it's unbelievable. So that's really zero. For all sake purposes, let's call this zero because it's closer than we could ever possibly get. And then we are going to say this, a big number, negative. Okay, this kind of matters a little bit more. A negative times a negative times a negative. So a negative times a negative is a positive, times a negative is back to a negative again. So this is 4 times negative infinity. 4 times negative infinity is just going to make an even bigger negative number, right? So that's going to be negative infinity. All right, kind of lost one. So this is 0 plus negative infinity is negative infinity is our answer. So it's going down infinitely. The further we go to the left, the further it's going down is basically what we're saying. All right, so that's basically how you're going to find your limits. So basically, it's going to come down to the horizontal asymptote. I kind of already had that discussion. And if you watch prior videos when we talk about rational functions, you have seen that when the numerator is less than the denominator, then basically when the degree of the numerator, which means, 2x to the 4th and 3x to the 5th, so when the numerator's degree is less than the denominator's degree, then basically it's always going to be 0. Always. Now, what do you do when the degrees are the same, like x to the 8th over x to the 8th? Now, what we did back a long time ago to find the horizontal asymptote is we just simply divided. We only look at that first term, the largest degree. And we just divide those. 12x to the 8th over 4x to the 8th. The x to the 8th cancel. 12 divided by 4 is 3. So the horizontal asymptote is 3. So basically, no matter where you're at, the answer will be 3. Because it's always going to keep... When you're going to the left and right for a rational, like I said, so I know the piece might not look like this, but... what we know is that both ends of a rational will always be getting closer and closer and closer to the asymptotes. The further you go towards infinity or the further you go towards negative infinity. That'll always be the case. Pretty much if you read the screen, it's exactly everything that I've been saying for the last 2 minutes. The only thing I haven't talked about is when the numerator is greater than the denominator. Now, there's no trick when that happens. In this first one, the answer is 0. I don't really need to go through that because I know the numerator is smaller than the denominator. Same thing happened in example number 2. The answer is 0. Now, here's a good example of something we haven't seen yet. Now, what do we do when the numerator's degree is bigger than the denominator's? Now, there's really no trick to here. So what you have to do is you have to try to make the denominator not have a degree of 0, basically. Have nothing but constants or, variables over constants. Or, I'm sorry, irrational. So numbers over variables. Now, so what I'm trying to say here is I take the degree of the denominator and I'm going to divide all of it. As long as I do it to everything, it really doesn't change anything. And I'm going to try to reset this so the bottom doesn't have a degree of 1. I want the bottom to have a degree of 0. That's essentially what I'm trying to do, to zero it out. So I'm going to take that x squared and divide it by x because that's the degree of the denominator. And I'm going to subtract 1 over x. Everything has to be divided by x. X over x and minus 1 over x. Okay, now if I can simplify that, that becomes just x. Can't really do anything right there. That becomes 1 minus, can't really do anything there. Now I can just think logically about the rest. Now what I could do is I could throw in some infinity signs here. So turn the x into infinity because that's what it's telling me to use. Minus 1 over infinity and 1 minus 1 over infinity. Now, thinking logically, like I just said a second ago, 1 over infinity, like 1 over a trillion. 1 trillionth is so darn close to 0, it's unimaginable. So we're just going to say that it's basically essentially 0. Close enough. And then this is also essentially 0. So now what do you have? We have infinity divided by 1. Well, anything divided by 1 is itself. So the answer is infinity. The further we go right, the further this graph is going up. That is what this tells us about its end behavior. That's what it's called at the end of a function. Now, this is a pretty easy question because all I have to do is look right here, and I can clearly see this answer is going to be 1/7. And that's simply because the degrees are the same. All I have to do is divide the terms of the largest of those degrees, or whichever ones are the same. And that's pretty much it. Thanks again for watching, and I'll see you on the next video. Have a wonderful day.